Right. Good afternoon, everyone. It's 2 p.m. Please confirm if you can see my screen and also if you can hear me. Good afternoon, Belinda. How are you?
Hi,
Great.
I'm well, thank you. I can hear you.
Awesome. Great stuff. All right. So, without further ado, colleagues, welcome once again and thanks for joining. Really appreciate your coming. So, we started on this awesome journey on statistical foundations for data science last week, and we're just going to continue again today, particularly getting into some of the mathematical stuff today, etc. And I think it's going to be exciting. So, yeah, I hope you managed to look at some of the work we talked about last week regarding, the importance of statistics, etc., the core foundations of what is statistics. We talked about that last week. So today we're really just going to continue in the same vein, but particularly the mathematical kind of stuff. Okay. So just a recap, perhaps you would see that this is really from session A up here. So I just want to recap some of these issues that we talked about, the probabilistic approaches that we're going to touch on at a later stage regarding, what we typically call Bayesian inference, etc. So this is a very simple formula, as it were, based on what we call conditional probability and, the idea of reversing probabilities or revising probabilities. So we would have defined here, I think in previous slides, A given B as probability of A and B divided by probability of B. But the argument here is that this numerator here can be rewritten in terms of what you already have, which in this case, the probability of A, we're assuming that that is known already. The prior probability of A is known. And in this case, we want to find the posterior probability or the updated probability given that B has already happened. So this is just a recap of some of the important things that we need to remember based on the definition of conditional probability. We'll be able to revise probabilities here. And this is the basis of what we call Bayes theorem, which is really the idea of updating probabilities. I see Prof is here. I hope I didn't jump the gun by starting before Prof's introduction. Okay.
No. Sorry, Farai. I was just 1 minute late. My apologies. Just keep going.
Thanks, Prof. Thank you. Great. Okay. But if you want to greet Prof, you can definitely do because I need to flip my computer in a minute. So maybe you can just greet the audience here.
Okay. Sorry, I didn't want to disturb. Yeah.
That's
No,
fine, Prof.
welcome everyone. The first installment of the mini school was a big success. So I'm pretty sure that today will be equally interesting. And I'm very grateful to Farai for going through all this trouble to present this very interesting school on a topic that is relevant to all of us. So Farai, please, without further ado, just keep going.
Thank you, Prof. Thank you. Great. All right. So, colleagues, so let's continue. I think I stopped around this place here, somewhere here last week. I didn't finish all the slides from session A, session 1A, but let me see where to kind of resume. Thank you. So, yeah, I think we stopped somewhere around here where we're talking about the idea of the unifying equation, which was the idea that we have a deterministic component and we have got a random component. And we're saying this is the kind of core idea that permeates within most, if not all, of the statistical models that you encounter in data science. Whether you're dealing with an artificial neural network setting or random forest, etc. The idea is there's always some irreducible error that you're going to encounter, etc. So there were some takeaways there. I just want to make sure that we covered everything, but you've got the slides. I think you can go through some of these issues. I want to jump into today's work, which is actually quite interesting because it's going to become a bit mathematical very soon. Okay, so again, maybe some learning goals to establish some mathematical building blocks for statistical thinking. And this is going to revolve around what we typically call probability distributions, etc. Probability theory, which is the foundational aspects of distributions, and defining what are random variables, etc. And then we'll talk about expectation variances and some sampling properties. But of course, things become very practical when you start talking about hypothesis testing. There's a lot of instances in data science where you need to compare if maybe some advertising campaign was effective, yes or no, and things like that. And you want to actually use some practical ways of testing those type of hypotheses. And this is where hypothesis testing comes in, and also confidence intervals, and equally likely, will play a big role there. Okay, so of course, connecting classical statistics to modern data science. I think that's the whole purpose. So this is kind of a recap again. We talked about this last week. The idea that the real world is not deterministic. There's a lot of randomness, and statistics helps us in formalizing this randomness, so that we can be able to model, predict, and control the presence of randomness. And of course, data science cannot happen without understanding uncertainty, and this is where the whole school is coming from. We're saying we can't do data science without statistics. That's what we're basically saying. Okay. All right. So maybe at this stage, it might be wise for me to just make this full screen as well, so that we're together on the same page. All right. So randomness. So what is a random experiment? Is there any process that can result in different outcomes? Imagine tossing a coin. It can result in a head or a tail, or throwing a die. It can result in 1, 2, 3, 4, 5, 6 if it's a six-sided die. The point is, at the end of the day, we're saying you cannot have a deterministic outcome. It's random. It's going to fall on different outcomes, in a random sense, not in a deterministic fashion where something is predetermined. And this is what we're calling a random experiment. And the idea of a random variable is actually now some form of a variable that assigns a numerical value to the outcome of an experiment. So it becomes very important. We are assigning some kind of numerical value, and based on these numerical values, you can be able to now to quantify how likely things are to happen, etc., based on the total number of outcomes, etc. So these are typical examples here: tossing a coin, rolling a die, and waiting times at a traffic light. Again, this is not fixed. It can be variable. That's the whole point. So probability as a measure of uncertainty, you can define probability in many different ways. This is an example of what we call the classical definition of probability. So there's subjective definitions of probability. There's other definitions of probability that you can talk about. But I think for the purpose of today, defining probability in terms of the classical definition, which defines probability as the total number of the outcomes that exist within that particular event that you are interested in, the number of ways that event can happen versus the total number of outcomes within the sample space, would call it. So think about a set here, S, and maybe you have your A here, you have 3 outcomes there, and in total, maybe you have 10, so maybe there's 7 outside of A. Then you're saying probability of A is equal to 3 over 3 plus 7, which is equal to 30%. I hope we're together there. Of course, there's going to be some properties of probability. And in this case, we're saying probability should be greater than or equal to 0. But technically, it should be also bounded by 1, right? But the idea of non-negativity and the total probability for the whole sample space, it should be equal to 1. It's a certain event that the event will fall within the sample space in this case. And of course, the idea of additivity, the sum of the probabilities is the union. Of course, we are assuming that the events here, A up to A, so maybe A1 up to A, K here, if you like, you're saying that disjoint. In other words, there's no common elements between these sets, okay? But there's a lot of other properties of probability that we could talk about. I think for today, let's just continue like that. So here's a typical example of a fair coin. I mean, if it's a fair coin, you're saying the probability of observing a head will be 0.5, and the probability of observing a tail will be also 0.5. Of course, it can't be a head and a tail at the same time, and this is the idea of disjoint probabilities. If you sum them here, they actually exhaust, we call it exhausting the sample space. So you could see heads and tails in this case as 50-50, heads and tails, 0.5, 0.5. Okay, great. Okay, let's move. Uncertainty, we talked about this last week. So I'm going to skip that. Then maybe we skip that as well. I just want to come here where we talk about probability in modern data science. So probability plays an important role in terms of sampling, simulation, inference, machine learning, and of course, ultimately decision making. All this relates to the use of probability in data science. Of course, if you're going to do some sampling, you want to, if you are talking about random sampling, you're saying every element in the sample is an equal probability of being selected like the other elements, etc. So you can see that the definition of the properties of sampling actually comes from probability. And of course, if you're doing some kind of simulation, which is very beautiful, simulation is really the idea of mimicking what reality could present in some kind of system, you know, whether it's in engineering or it's in finance, etc. I mean, in finance, there's a lot of simulations that happen as well when you're doing stock price models, etc. There's a lot of random number generation that happens and all that. And it really builds a lot on probability theories and probability concepts. Of course, inference is a probabilistic child, really. I mean, if you're going to make statistical inference, things like hypothesis testing and estimation is based on what we call the sampling distribution of the mean. I think I touched on this last week when we said, you know, imagine you have a population and you take random samples. And in this case, you are repeating the sampling procedure. Now, instead of having a distribution of maybe X, now you want to have a distribution of X bar. The distribution of the sample means. I mean, this is a beautiful thing that I've drawn here already. I don't know if we'll be having enough time to touch on this, but I mean, the idea here is if X follows maybe a normal distribution, we'll talk about the normal distribution very soon. Then X bar also follows a normal distribution, in this case, mu sigma squared over n. It will have a less variance. But the point is, all this is coming from probabilistic thinking. So we're going to jump into distributions very soon. Okay. Probability is the mathematical foundation for all statistical reasoning, really. Without probability, there's no statistical reasoning. There's no statistical thinking. And random variables quantify uncertain phenomena numerically. Probabilities are consistent, coherent, and measures of belief and frequency. Of course, I think the classical ways of looking at probability and the Bayesian ways of looking at probability are slightly different, but I guess for a statistical foundations course to data science, we don't need to emphasize that too much. Okay. So at the end of the day, we're saying probability distributions. Someone might ask, what is probability distribution? So these are now theoretical distributions that have been proposed, you know, to describe some behavior that exists in practice. You know, if you're dealing with waiting times, for example, waiting times until maybe if the customer's purchase or things like that, it's theoretically justified that you can use a certain distribution, probability distribution, to analyze that type of variable. If you're dealing with the weight of people or the length of, some distance between potholes, you know, you can deal with some particular distribution, in this case the exponential distribution. If you're counting the number of potholes on the road, I was hoping that this was going to be a joke, but it looks like it's not too funny. That will be the Poisson distribution. So what is the idea here? The idea is understanding the idea of statistical distributions become very important, because if you want to quantify how likely things are to happen in a particular setting, you can actually just understand the fact that, okay, this variable is distributed by this type of distribution. So I will assume that what I'm dealing with here is the normal distribution, and then you use the normal distribution to calculate the probabilities. That's the type of approach that we're dealing with here. So probability distributions describe how outcomes of a random variable are spread out across possible values. Okay, whether they are uniformly, whether they are symmetrically spread like that, like in a bell-shaped distribution, or they are uniformly spread out there, or or we have gotten some kind of exponential and things like that. Someone says the portal issue is emotionally not funny. Okay, emotionally they're not, yes, but I think statistically they are. So, what is the likelihood of observing a particular value or range of values of x, for example? So, these are the type of questions that you can ask. So, we'll be dealing actually with an area under the curve. So it becomes a bit mathematical, but the maths is very easy. The maths here is just area under a curve. So you see very soon when we start talking about distribution. In this case, this could be, if that was x1 and here we're dealing with x, this would be the probability that x is greater than x1. So you can quantify that area. Okay. Of course, one can see that this area will be the complement of what I'm just shading there. So you could actually see that as 1 minus probability that x is less than or equal to x1. So this would be equal to probability that x is greater than x1. There's a good reason why sometimes we use the less than sign, because we kind of accumulate these distributions, particularly the continuous distributions. There's a way we accumulate them from negative infinity. In this case, for the normal distribution, would accumulate, from negative infinity all the way up to x, and we have some form of integral there. I'm not going to bother you much with that. Okay. So in data science, understanding the underlying distributions of data informs modeling, assumptions, feature selection, outlier detection, and algorithm selection. And this is the point. I hope we're together there, colleagues. This is the point. So if you are going to do good data science, you want to also have an understanding of what is the underlying distribution of this data, etc. There's actually models that rely on normality in the variables you're dealing with, etc. So if you're going to use such models without you testing for normality and things like that, then you are not doing good data science. That's the argument we're bringing here. Okay. So discrete distributions. We can talk about discrete distributions. The difference between discrete and continuous. Think about discrete as count variables, right? Count variables where you kind of maybe you want to count the number of potholes, like I was saying earlier. That's a discrete variable. That's a discrete type of variable. But if you are going to talk about the length between successive potholes on the road, that becomes continuous. Okay, so the count variable will be like your typical 0, 1, 2, 3 type of thing. Okay, number of potholes or number of customers entering a shop, 0, 1, 2, 3, 4, etc. But then if you talk about the time, the waiting time between customers, that can be seen as exponential. And that will be continuous. So when you're talking about discrete distributions, we're talking about distributions that relate to discrete variables. And in this case, we'll talk about what we call a probability mass function. So probability mass function is really just a function that assigns probabilities to the different outcomes within a discrete variable. Okay, think about a coin that is fair. You have a head, you have a tail, and you say here is your x, and then here is the probability of x. For the head is 0.5, for the tail is 0.5. That's an example of a probability mass function. If you're dealing with a die with 6 sides, you'll be dealing with maybe x 1, 2, 3, 4, 5, 6. Sorry. Then you have your probability of x here, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. You can see that the principle here is the total probability is actually going to be equal to 1. The same thing here. If you add this 6, you'll get 1. Okay. So we can have examples of what we call also the binomial distribution. This is just a collection of what we call Bernoulli experiments. So Bernoulli experiments is a Bernoulli experiment is an experiment that yields two possible outcomes. Whether it's a yes or a no type of thing, failure or success. But then when you repeat that n times and the probability of success is fixed, then you talk about a binomial binomial distribution. This becomes very important actually in data science as well. And of course, the Poisson. If you want to really be on par with discrete distributions, at least understand these two. I mean, the binomial and the Poisson, you really just need to understand this. Maybe do some pen and paper examples as well regarding binomial and versus Poisson. But the Poisson is the one I've been talking about all the time, actually, when I was talking about potholes. So if you want to talk about the count of things like customers getting into a shop, when the rate of occurrence is defined, that is where the Poisson distribution comes in. The Poisson distribution is really a distribution that quantifies, the number of expected outcomes given a certain period of time, maybe the number of potholes after 5 kilometers, given that there is a rate of occurrence of potholes, like maybe there is a pothole every 200 meters, so the Poisson distribution can handle that. Okay. Great. Continuous distributions. So the idea here is we start talking about what we call probability density function, PDF. So the probabilities are going to be assigned by what we call a PDF. But the point now is we've got infinite possibilities of X. We've got infinite possibilities of X. So we can't really assign a probability to one value. In fact, that is going to be 0. So we're going to now talk about the probability that X is going to be within a particular range. The probability that X is going to be within a particular range, and we'll define that as follows. Like if you look at this part here, where we're saying the probability that X is between A and B. So think about maybe a distribution that looks like that, and you've got your A there, you've got your B there. So that probability we're talking about here is actually the area of this shaded region here. I hope that is clear. Okay, so this is the type of thinking that we'll be having there. So technically, if you go back to integration, you see that the area that we're dealing with here is just the integral, right? The definite integral from A to B, f of x dx. Okay, but in data science, you're not going to be doing it this way, right? Sorry, something jumped there. You're not going to be doing the probability calculation using an integral like that. You are going to be using maybe a probability density function, which is already accumulated, the CDF, etc. And of course, if you're using Python and R, you're not going to be even writing the formula itself. You're going to be just using some function, which is predefined in a package. But again, what we're trying to say here is the understanding of the maths or the mathematical foundations behind it is very important. You want to be able to know what is happening within the black box before you play around with the black box. That's the kind of approach we're taking here. I hope this is clear enough. Okay, so examples, the height or weight of individuals, which is typically normal, waiting times between events, that's exponential. The waiting time until Farai's next jog. I know there's people who are waiting for my jokes here. So the waiting time before I drop another joke there, that's exponential, right? And the number of jokes that I'll be making here, you can see that as Poisson, right? Time to failure. The Weibo and the Gamma, they do a very good job. So this is actually very important if you're dealing with what they call reliability analysis, where you're talking about things like, until when, what is the probability that the equipment is going to fail maybe within the first 5 years. I mean, it's a big equipment you're buying, and you want to analyze what is the probability that it will fail within the next 5 years. What is the probability that, someone is going to die before they're 45. I mean, this sounds like a very scary thing for me to be saying, but this is what actuaries do, by the way. So I mean, this is good business for insurance companies, right? They need to know how likely it is that you survive after 60 before they can offer you a product. Again, this is not a joke. I see people are not laughing, but you can see the importance of probability distributions, right? Okay. So time to failure, that can also be seen as time to death, particularly in this case, we're talking about mechanical failure, but yeah, sure. Okay. Okay, cumulative distribution function. This is now what we call the CDF. So really here, the idea is to accumulate the probabilities, up to a particular point. So we want to accumulate up to a particular point. You can see we've got a capital F here. The idea why we've got a capital F here, where we had a small letter f in the other instance, is that we've got a capital F now because we have now integrated the small f's, okay, up to a particular point. And in this case, we're using a t there because we want the formula to eventually have x here. So for the formula to eventually have x here, we want to integrate up to x. I hope you can see that. So that when you do your gymnastics in integration, etc. I mean, technically for a statistical foundations course like I'm doing, I mean, the assumption could be also that you've got a bit of mathematical foundations. In this case, maybe differentiation and integration. But if you don't have, I mean, don't stress, colleagues. I mean, all we are saying, this thing is just saying sum all the values. You're summing all the values type of thing, you know. And I think this is where we're coming to. The idea is, if you have a distribution, you're saying from the negative infinity there, coming all the way up to a value of x, you want to find that area. And this is what we're calling f of x. I hope that makes sense, everybody, which is the probability that x is less than or equal to x, small x. Yeah. So this is a capital X. Maybe I can do this to make it clear. Small x over there. Okay. Good. All right. Expectation, very important stuff. The idea of an expectation is the idea of the mean. So what do you expect to see? Think about that type of analogy in English. What do you expect to see? You expect to see the average, you know. So the idea of an expectation is really, I think in the discrete sense, we talked about this last week where we said it will be, you know, your x bar is equal to summation from I is equal to 1 up to n of xi, right? So you divide that by n. But in this case, we're saying, if you think about the expectations really here, in a continuous sense, it's really the integral from negative infinity to positive infinity of x f of x dx. So what is the argument here? The argument is very simple. The argument is actually very simple. We're saying we've got x values, so many of them, and we've got the probabilities, which is the f. F is the probability, remember, probability. And here is your values. So if you multiply the value times the probability, and you do that for all the values, you sum for all the values. You find the sum of this for all the values. Value times probability. Remember, the probability is like a weight. Think about the probability as the weight of how often that value is appearing. So if you multiply the value times the weight, the value times the weight, and you find the sum, effectively, you're actually coming to the average. Why are we coming to the average? Think about this from this point of view. I think I gave you this earlier. 1, 2, 3, 4, 5, 6. 1 over 6, 1 over 6, 1 over 6, 1 over 6, 1 over 6. Okay. So if it's multiplied this by that, that by that, that by that, etc., you find that here you get 1 over 6. That becomes 2 over 6. That becomes 3 over 6. 4 over 6, 5 over 6, 6 over 6. If you find the sum of these, what are we going to get? 1, 3, 6, 10, 6, 10 plus 6, that's your 16 plus 5, that's 21 over 6. And this gives you 3.5. If you think about it, the average of these values is actually 3.5. Because here in this case, we're saying they're all appearing one at a time, right? They're appearing once. So effectively, you can see with this simple example that the idea of an expectation is actually a powerful idea. Of course, this was discrete, but here in the continuous sense, we're saying you just have to integrate the values times their probabilities, and that gives you the expectation. There's mathematical proof to this, but I guess the mathematical proof is not part of statistical foundations, really. Okay, so the variance is defined this way. Variance being, of course, the sum of the squared, or rather the average of the squared differences from the mean. You want to find the average of how different your values are in the squared sense. So y squared, I mean, technically, if you think about 1, 2, 3 as values there, you would see that maybe X bar here is 2. If you subtract the mean from all the values here, you get -1, that you get, the year you get 0. 3 minus 1, you get a 1 there. If you were going to sum these values, you would actually see that it becomes 0. So that might actually mislead you. You might think, the values are not different. Why? Because the average deviance here is actually 0. But then the idea of the variance says, let's square these values. Okay, you square those values. And that's what the idea of squaring that comes in there with the variance. I hope that is clear. So the idea of the variance is really saying, let's find the average of the squared values from the mean, the squared distances from the mean. Y squared, we could have taken absolute values. In this case, to deal with the negatives, we would have taken absolute values. But the calculus around absolute values is very complicated. So what we end up doing is we take squared values, okay, squared values. And now, when you go to the standard deviation, we have to go back to the original units. Remember now the variance, if this was distance, if these values were distance in kilometers, if this was distance in kilometers, then the variance is going to be kilometer squared, kilometer squared, kilometer squared. So effectively, how would you interpret kilometer squared? That's nothing but area, right? Or, in this case, kilometer squared, maybe area. But if it was rand squared, how would you bank rand squared? I don't think there's any bank that would accept rand squared. If you try maybe today, that would be great. But my joke is not as funny as I thought. I see people are not laughing. But at the end of the day, we're saying you've got to find the square root of the variance for you to have something that is interpretable or something that is usable, something that is on the same units as the mean. And that is what we call the standard deviation. So the standard deviation is nothing but just the square root of the variance. And the beauty of the standard deviation is it will be on the same units. It will have the same units as the standard deviation. Are we together, everybody? It will have the same units as the mean, sorry, not the, yeah. So effectively, we're saying you can actually say mu plus or minus sigma, and this brings you somewhere. We will talk about this a little later on when we talk about confidence intervals. All right, this is very important. Higher moments, you can talk about other moments. So effectively, these things that we talked about, these are the first two moments, the mean and the variance, etc. What do we mean by moments? You can see here we're raising to the power of 2. The moment you go to the power of 3, we're saying that's a higher moment. The moment you go to the power of 4, we're going to a higher moment. I won't bother you much about that, but the idea of skewness is very important. You need to know when distributions are skewed. So if you have a distribution like this is symmetrical more or less. But if you have a distribution like that, that's skewed to the right. If you have a distribution like that, that's skewed to the left. Okay. So the way you deal with skewed distributions, you must be very careful. Okay. Of course, income, for example, is right skewed. A lot of us lie here, right? This is not a joke. Okay. But you find that there's very few people who are very rich, right? And of course, I think this type of distributions are very important for insurance companies as well. Insurance companies, they deal with a lot of this type of distributions, even for insurance claims. A lot of people claim small claims, right? There's very few claims that are very big. And these are the claims that can actually sink the insurance company. And this is where you find the idea of reinsurance, for example, where the insurance companies got to insure also for these big risks, right? Are we together, everybody? Great. Let's move. Okay, some kind of linear operators there in terms of linearity and variance not linear. It's not linear. There's no linearity with the variance. But then the idea of independence that becomes very important as well. The idea of independence, statistical independence. I touched a bit on this last week. I think we touched on dependent variables when we talked about, or rather independent variables, when we talked about the definition of conditional probability of A given B is equal to probability of A if A and B are independent. I think we talked about this last week, right? Yeah. So because you find that if A is not dependent on B, then conditioning A on B does not affect A. Okay. Again, you can see this from the definition. Probability of A given B is supposed to be probability of A and B over probability of B. But we're saying here, sorry, something's jumping. We're saying if they are independent, then this will be probability of A times probability of B over probability of B. And this cancels. And then you go back here. Okay, independence. But then with regards to variance, then some that follows as well. So the algebraic properties of expectations, etc., they're very important, particularly if you're going to talk about proofs, etc. in data science. But I wouldn't bother you much about this because I guess data science is really not about proving statistical concepts, etc. I think the understanding of how it works and etc. is more important than the why. Yeah. Okay, let's get into some common distributions. The Bernoulli, we talked about this a bit. Binary outcome, success or failure. Success in this case does not denote something that is morally, successful in the ordinary sense of the word success, right? So success could be contracting a disease or something, could also be seen as success in this context. Okay, so the probability of success being a P there. And of course, you can talk about 1 minus P being the probability of failure. And once you have a sum of Bernoulli trials, you're dealing with a binomial, typically with N trials, right? N trials, then, you have your binomial formula there, which is beautiful, actually. N select X. In this case, you have your P to the power of X. You have 1 minus P to the power of N minus X. I mean, this is a beautiful formula, actually, to think about where this formula comes from. It's just a very simple formula. It's coming from independence. We're saying these are independent trials. So you've got X successes. So you've got, but this is the probability that X is equal to small x. So, you're thinking about X successes, right? So you've got the probability of success being a P. Probability of success being a P. So you're saying P must be raised to the power of X. Why? Because you are having X successes. So P times P times P times P. How many times? X times. And then you have got failures, probability of failure, 1 minus P. And how many failures do you have? If you have X successes and you have N trials, then N minus X is the number of failures. So the probability of failure being 1 minus P, you raise 1 minus P to the power of N minus X. But then the point is, these arrangements of the successes and failures, or rather successes and the failures, can be rearranged in many different times. How many times in this case? N choose X, which is also N select X. I hope you see where the formula is coming from. This is just a bit of mental gymnastics, but I hope that was beautiful. Then the Poisson, we talked about the Poisson. Very nice formula that emerges also with an exponent somewhere there, but I won't bother you much about that. The normal distribution, is a continuous symmetric distribution defined by two parameters, the mean and the variance, or the mean and the standard deviation, if you like, sigma there. Okay. The normal distribution, very important. This is one distribution that if you're going to go into a data science interview and the interviewer asks you, do you know the normal distribution? And you say you don't know, I think it could be a sign that you didn't get the job. Of course, I'm joking, but if you don't know the normal distribution and you are doing data science, I think you want to maybe work on a few things. Yes, it's very important. It's a very important distribution in, although a lot of practical things are non-normal, but I think at least understanding the normal distribution gives you a good idea of what happens in data science, I think, particularly with regards to assumptions in models. There's a lot of models that assume what we call normality. Okay. So the exponential distribution, waiting times, uniform distribution, equal probabilities within a range, etc., etc. So the normal distribution is got the one with the mean of 0 and the standard deviation of 1. That's the standard normal. The standard normal. So the one that you now standardize is a beautiful one. So you're saying you've got infinite versions of infinite distributions that can be normal. based on the fact that you've got various combinations of mu and sigma that you can have for the normal distribution. But we're saying you might want to standardize all that. Think about the US dollar type of thing, right? You want to have a basis currency that you can compare other currencies to, type of thing, so you can have a standard normal distribution. That's a very beautiful idea, but then it will be having a mean of 0 and a standard deviation of 1. Okay, and the good thing is the probabilities associated with the standard normal distribution have already been characterized and in tabular form, etc., etc. So you'll be able to transform any other normal distribution to the standard normal distribution. So each distribution defines the likelihood function in a sense. That's the nutshell. And hence some natural loss function. We want to understand their properties to design appropriate cost functions, particularly for machine learning, quantifying uncertainty, etc. Conceptual takeaways. Distributions describe how uncertainty is structured, within the data you're dealing with. PMFs, PDFs, CDFs are all mathematical tools to measure and visualize the structure of your uncertainty. Expectation and variance summarize the center and spread. These are some of the two most important things that you want to understand with regards to your data. Where is your data centered, and how do the observations vary from the center? Are we together? Where is your data centered, and how do the observations vary from the center? I mean, before you do any complicated stuff, you want to understand this. And this is what you typically do in what you call EDA. But in a statistical sense, it's just what we typically call descriptive statistics, right? So exploratory data analysis. So the idea is before you do complicated analysis of your data, you want to look at your data, and how do you look at your data? Through summaries, through frequency tables and things like that. And this is where you get all the importance of expectations and variances, etc. So distributional thinking is essential for understanding error, bias, and generalization. Of course, it's looking at the big picture. You're looking at the big picture. In this case, we're saying it's not theoretical caps. These are like structures beneath every data set. We're saying, what could be the typical data generating process? Where could the data have resulted from? That's the question we're trying to ask. Where could the data have resulted from? Okay. Probability distributions describe how data behaves. They form the mathematical foundation for modeling randomness, uncertainty, and variability. This is a key thing for any data scientist. I've always said to my students, if you go to an interview and they ask you about data science, etc., and they ask you things like distributions, etc., and you don't know, maybe we also don't know each other, right? But this joke is not too funny, I know. But the point is, it's very important for you to understand this if you're going to be a good data scientist, because there's no company that is going to expect a data scientist to be having a black box where you throw things and you do magic and you don't know what is going on. So the idea of understanding, the distribution of your data, etc., etc., these are key concepts before you get into, complicated Python programs, etc., etc. All right. I think this is just a further description of the distributions with a bit of math there. I'm sure you can see that it gets a bit interesting, right? Binomial, this formula I just wrote now. You have your expected values, you've got your variance there. This can be derived, but we're not going to bother you with that. Don't stress about that. An example is the number of positive responses from 100 customers. That's very practical, right? In this case, you say you're sending 100, maybe invitations for something from customers, right? And in this case, you want to say, what is the probability that we have so many positive responses? You can actually calculate and quantify that probability. That's beautiful, isn't it? Okay. Then we can talk about the normal distribution again. The idea of the central limit theorem, which is a very important theorem, which I can just talk about briefly. So the idea is, if you have got a population, even if your values here from the population are non-normal, think about X here, which is some kind of a skewed distribution like that. If you're going to come here to this population and you sample and take samples, and each sample here, we're saying if each sample actually has n greater than or equal to 30, n greater than or equal to 30, n greater than or equal to 30. In this case, maybe n is 40 or something. We're saying when you take those sample means, even if you're coming from a non-normal distribution, the moment you start drawing the sample means here, assume you know the mean of this distribution here is mu. The point is, if you start drawing the sample means themselves, they're going to have a normal distribution. Isn't that beautiful? That's one of the most beautiful things that happens in statistics. So if you come from a non-normal distribution and you sample samples that are big enough, how big? Greater than or equal to 30, and you find the average of those sample means, you find that the average of those, sorry, not the average of the sample means, but the average of the sample observations, you find the averages of those sample observations. Those averages are going to form a bell-shaped distribution. Even though you're coming from a non-normal distribution in the actual value of x, we're saying that x bar here is going to have a normal distribution. And this is what we call the central limit theorem. This is one theorem that if they're looking for what they call a data scientist, statistical data scientist, I've seen that they're starting to use that term now, statistical data scientist, someone who's a data scientist but also understands some statistical concepts. I mean, they might ask you a question like this: what is the central limit theorem? So in mathematical terms here, we're saying if x comes from maybe an exponential distribution with a parameter lambda here, such that you know the mean of x. We're saying x bar will follow the normal distribution. Are we together? If n is greater than or equal to 30. Of course, we can determine the parameters there. That's what we call the central limit theorem. We're saying sample means approximate normal, even if the data is not. This is a very important distribution. Maybe I should pause there on the central limit theorem. Central limit theorem. Very important theorem in statistics. The core, it is actually the core of most of statistical results. Okay, the exponential distribution. This is the one that I was talking about for waiting times and survival times, etc. It's very important in modeling, you know, how long things take to happen, etc. So you're dealing with time here. And it works well with the Poisson because the count will be Poisson, the waiting time will be exponential. So you can just about imagine that there will be an inverse relationship between the Poisson and the exponential. There will be an inverse relationship because we're saying if the waiting time goes up, then the count goes down. I hope you can all agree with that. I hope you can all agree with that. So if the waiting time goes up, in this case, if the waiting time goes up, what do you mean by waiting time? Waiting time between customers. If it takes long for people to arrive in the shop, then you can imagine that there will be few people that would have visited the shop at the end of the day. Okay, so there's an inverse relationship between the exponential and the Poisson. If the number of customers arriving goes up, then the waiting time will be going down. Okay. I think there's another mic that is unmuted. Maybe we might want to check that. Yeah. Maybe, yeah. There's another mic that is unmuted. Let's try and mute it. Okay, great. Great. So the Poisson is here. Okay. Beautiful exponential formula there. It's actually a very foundational distribution too for some of the what we call generalized linear models. And in this case, we're talking about the number of transactions, number of customers, number of emails, number of something. Are we together, everybody? How we can see that? It's a beautiful distribution. So it's not poison, right? I think that's one thing you want to avoid as well as a data scientist. If you're going to be a good data scientist, you don't want to be sitting in a group and say the Poisson distribution. It's a Poisson distribution, and it represents I think it's fish in French, if I'm not mistaken. I see people love that joke. Okay, great. So other useful distributions include the uniform, the gamma, the beta. There is hundreds of distributions. There is a lot of distributions, and you might be interested in checking a lot of these other distributions. There's good summary things that you can see. Sometimes people connect the relation between this distribution and that distribution. I mean, it's just a lot of distributions, but they're all kind of generalizing what you can expect within some particular phenomena, etc. Chi-square distribution, also very important. Student T, very important again in hypothesis testing. Whenever you have small samples, student T distribution is a very important distribution. The guy who actually developed this was called William Gosen. He was working for a company that didn't want people to use their names, etc. So he used the student name. He called himself Student T. It's kind of a joke, but it's an interesting joke, I think. Yes. So the link of distributions to data science, when you're talking about likelihood functions and loss functions and simulations, like we talked about earlier, these all revolve around, probabilistic quantification of how uncertain things are to happen, etc., etc. So a lot of machine learning algorithms optimize likelihoods, how likely things are to happen, and these all derive from statistical distribution type of thinking, etc. Monte Carlo method. This is very important, by the way. If we happen to have people here who are doing research, which I think there is, I know there's people who are trying to do data science for job purposes, and maybe you want to, build some statistical foundations so that you can go and work at a bank, which is also beautiful. I mean, Monte Carlo methods, they are everywhere. They're even also in finance. When you're dealing your quantitative finance stuff, you would want to also understand what is Monte Carlo. But if you are doing research, those who are doing research, if you are going to employ Monte Carlo methods, maybe in environmental studies and stuff, you can stand a good chance to publish in top tier journals, I guess. Monte Carlo methods are very beautiful. They use them in many aspects, even in integration. If you want to estimate some area of some sort, you can use Monte Carlo methods. It's again probabilistic ways of calculating areas, etc. So the idea behind Monte Carlo is really the idea of exploiting randomness. You want to exploit randomness to quantify something. And it's a very beautiful idea. So it works as well, as good as, your typical optimization, but then from a probabilistic or a randomness way of looking at things. Law of large numbers, I think I'm going to skip this. I see it's just after 10 to, let me try and see where we can stop. I was going to touch a bit on estimation, but I mean, we're not really pushed for getting into other deeper stuff today. Maybe we should pause there because it looks like last week we went beyond the time with regards to questions. Maybe let me pause here so that we can have 7 minutes for question. How is that? How is that, Prof?
Thank you very much, Farai. That was great. Again, thank you very much. Thank you.
Thank you, Prof. Thank you.
Farai, I will give the participants a second to think about questions. Some people asked about the slides.
Yes.
If you share them with me, we will upload them on the website.
Yes, great. So for last week, I think I shared with was it Renee? I think it was Renee for last week, but I shared I think a couple of days ago. So I think
Okay. If you
maybe they're
share it
already
with,
processing. Yeah.
okay, if you share it with her, it's fine. It will
Great.
appear then on the website soon. Yeah. I will
Awesome.
follow up with her. Thank you very much. Yeah.
Great.
And also, after somebody asked in the chat whether the session is recorded, yes, it is recorded. We will put it again on our YouTube channel.
Yeah, good.
Any questions?
It looks like there's a few questions on the chat there, Prof.
Okay, sorry. Let me see. Good afternoon. Okay, that was thank you. Understood. The other question was, what is preferable in application when dealing with data gaps?
Data gaps. What is that? Data gaps. Are we talking about missing values or what? Caroline, what is data
I'm
gaps?
not sure. It's a question by Caroline. Yeah.
Yeah, Caroline. Data gaps. You want to vocalize that perhaps, Caroline, or you want to explain it in chat again? I don't know. Data gaps.
Okay, maybe there's another question here that maybe is easier.
Yeah.
What are the applied differences between binomial and Bernoulli distributions?
I mean, look, the binomial was really just a combination of Bernoulli, right? Bernoulli trials. So you are basically saying if the experiment happens once, then it's a binomial experiment. But if it happens more than once and it's a fixed number of times, you're dealing with a binomial distribution. I hope that answers the question. Yeah.
Yeah. No, thank you very much.
Thank you, Prof.
And maybe one other question here is it fair to say that Bayes' theorem doesn't work if the variables are independent?
Look, I get where the question is coming from. It's coming from the fact that we were saying that we're updating the probabilities. So in that sense, you can think about it that way, yes. But remember, it's not about whether variables are independent or dependent. I think what Bayes' theorem is really trying to bring here is the fact that you want to update the probability. Yes, of course, if the events are independent, there's nothing to update. I mean, there's no condition. The conditional probability does not depend on the occurrence of the other event. So in that sense, you are right. But I think Bayesian thinking goes beyond two variables. It goes beyond two variables. I mean, it goes into Bayesian inference, etc., which could be a bit more complicated than just dealing with two variables. Yeah. But I mean, Bayes formula, yes, you are right. If you're talking about Bayes formula, yeah.
Excellent. And in the Q&A, an anonymous attendee wrote, thank you, Farai, for the presentation. I have a statistics background. How can I launch into data science in practice?
That's a good one. I think this is what we're going to do with Prof's permission. Maybe next year I'll do another mini school on, maybe from statistics to data science.
That sounds great. I will make a note.
I think from statistics to data science. I think that's now. I think the other side of the coin we're dealing with here. That's now, the coding. That's now the. So I mean, if you have a statistics background, you have got a solid foundation. But now I think what you just need to do is to get into the coding. You want to get into the R, into the Python, etc., etc.
Yeah.
Like they always say, that Prof. They say a data scientist is a statistician who is good at programming than an ordinary statistician, or a computer programmer who is good at statistics than an ordinary programmer.
Excellent.
So yeah,
But
sure.
that is probably a topic for another talk.
Yes, yeah.
As is someone mentioned here again, are we going to include data visualization? I think that will be the topic of another mini school. And we had some, if you go on the NITheCS website, you will find that in the past we had similar mini schools on visualization. And if this is a topic that is interesting to people, we will make an effort to organize one soon.
Yes.
Yeah. Okay, very much. Thank you very much. Then
see a question there, Prof. I see an interesting question there from, who is that, Golo? Prof, you saw that one?
Which one?
The one that talks about how to deal with data that is not normally distributed.
Okay,
So,
okay. Just came while we were talking. Yeah, please. If
yeah.
you would like to answer it, you're most
Yeah,
welcome.
that's a good one. That's a good one actually, because the point is, there's ways of normalizing data. So there's some transformations that you can have, like the box transformation, etc. You can normalize data. Golopeng, yeah, sure. And of course, if your data, if the model assumes that the data must be normal, then you want to make sure that the data is normalized. And yeah, there's transformations that you can use. In fact, it was part of the slide somewhere, but I probably just didn't touch on it. Yeah.
Excellent. But I'm looking at the time. All
Yes.
good things should last an hour.
Sure,
Yeah.
sure.
Yeah,
Exactly.
no, I'm just
Exactly.
joking. So, Farai, thank you very
Yeah.
much for a great lecture.
Yeah.
And you see, we
Thank you,
had
bro.
again a large number of online participants, and I
Yeah.
see lots of clapping and
Yeah.
hearts and other symbols that I don't know what they are. That I'm sure that means
Sure.
that they're all
Sure.
very happy.
Sure.
Yeah.
Sure.
So, Farai, thank you very much again. I will check, make sure that the lecture notes of last time get uploaded,
Yes.
the slides. And if
Yes.
you send me these, please copy Rene and me so we make
Yes.
sure that our webmaster uploads them promptly. Yeah. So that
Great,
we
Prof.
can
Awesome.
review them before the next lecture. Yeah.
Great stuff.
Right.
Great.
Thank you so much again. It was a wonderful choice of topics and a very nice presentation. Yeah.
Thank
And
you, Prof.
we will share the YouTube link and you will become a YouTube star. Yeah.
Thank you for that. Cheers, bro. Thank
Thank you
you.
very much.
Thank you.
Have a
Bye.
good afternoon, everyone. Thank you.
Bye.
Bye-bye. Bye-bye. Cheers.